This presentation provides an introduction to Earth's history. We'll zoom through 4.6 billion years of geologic time in the next 6 or 7 minutes.
We have one major learning objective for this lesson. We want you to be able to explain how the primitive Earth formed, describe how it developed its oceans and atmosphere, and discuss what early life looked like on the planet.
Earth's history can be divided into 3 big chunks of time we call eons. During the first 2 eons, the Archean and Proterozoic, the planet's barren surface would have looked much different from today, with no plants or animals on land and no fish in the sea.
It was only during the last 12% of geologic time, during the Phanerozoic eon, when Earth began to resemble the planet we see around us today. As we move through this presentation, keep an eye on the timeline along the left margin of the screen as an indicator of where we are in Earth's history.
Earth formed about 4.6 billion years ago as our solar system was forming from a collapsing cloud of dust and gas.
The remaining materials organized into a flattened disk of rotating debris. Gravity from larger clumps pulled in adjacent dust and rocks to form planetesimals, which eventually collided together to form the early Earth.
Hot young Earth was characterized by widespread melting and rapid separation of the internal compositional layers of mantle and core within the first 30 million years of the planet's life.
Volcanic gases, including water vapor from Earth's interior, formed a new atmosphere by outgassing processes. The planet's surface was too hot for liquid water, resulting in a constant cycle of precipitation and evaporation.
Relatively early on in Earth's history, there was a collision with a smaller Mars-sized planet that blasted out the material that came to form the Moon. This resulted in planet-scale melting and differentiation of the crust.
The very first atmosphere was helium and hydrogen left over from the formation of the planet. These light gases were quickly lost to space. Then outgassing from volcanic eruptions contributed to a secondary atmosphere, which would have differed substantially from the air we breathe today.
There was no oxygen and high concentrations of carbon dioxide, ammonia, and methane. Differentiation of Earth's core resulted in the development of a magnetic field to protect this new atmosphere from solar winds.
About 4 billion years ago, the inner planets, including Earth, were subjected to a bombardment of comets and asteroids. These impacts transferred water to Earth that contributed to the early oceans. The rest of the water came from outgassing volcanic eruptions as the hot Earth cooled.
All life on Earth is cellular, and the most primitive life is represented by prokaryotic cells, such as bacteria, that are less than 1 micron in size.
The early atmosphere was modified by 2 processes. First, bacteria evolved to use photosynthesis to consume carbon dioxide and produce oxygen. Second, sunlight broke down ammonia to form nitrogen and hydrogen. The hydrogen was lost to space while the nitrogen stayed around to form the major components of today's atmosphere.
Communities of cyanobacteria precipitated limestone between cells to form algal mats that created mound-like structures similar to the modern stromatolites in this image.
So early bacterial life in the ocean starts to consume carbon dioxide and produce oxygen by photosynthesis. But as we will see next, none of this oxygen makes it to the early atmosphere, which was dominated by nitrogen and carbon dioxide.
Banded iron formations, or BIFs, are the most common sedimentary rocks formed during the Archean. These are chemical sedimentary rocks formed when oxygen reacted with dissolved iron in the early oceans. This process continued until all the dissolved iron was oxidized. This took more than 1 billion years.
It was only then, when the dissolved iron was used up, did oxygen become available to be added to the atmosphere. Gradually over time, the carbon dioxide concentration in the atmosphere was reduced and the oxygen and nitrogen levels increased.
Multicellular organisms first appeared around this time in the early Proterozoic and represented a fundamental biological change. These were larger than prokaryotic organisms with more complex internal structures. Eukaryotes consumed oxygen and produced carbon dioxide, so we can infer that oxygen had begun to accumulate in the atmosphere, albeit at low concentrations.
Little happened for the next billion years as Earth's early continents amalgamated into a relatively stable supercontinent. This has been dubbed the boring billion, because these modest changes in the plate tectonic cycle resulted in few changes in Earth's atmosphere, hydrosphere, and biosphere.
Life was a mix of single and multicelled organisms living in an oxygen-deficient ocean. However, the breakup of the supercontinent Rodinia kicked off a series of dramatic changes beginning around 750 million years ago.
There is extensive evidence of glaciation in the rock record from around 700 million years ago. During snowball Earth, it is thought that only the lowest latitudes around the tropics didn't freeze over.
Geological evidence has been interpreted to indicate that the planet seesawed back and forth between the extreme cold of snowball Earth and the warmth of hothouse Earth conditions, when no ice would have been present. It's thought that these conditions alternated twice during about 100 million years.
Some potential reasons for such significant climatic contrast include changes to the output of the sun, fluctuations in the carbon dioxide concentrations of the atmosphere, or changes in ocean circulation.
Around this time, oxygen was more abundant in the atmosphere at about 50% of its current concentration. Changing global conditions were about to spark a great surge in evolution and the development of organisms with hard skeletons that would be readily preserved as fossils.
Fossils became much more abundant in the rocks of the Phanerozoic eon, representing the last 542 million years of geologic time. The presence of fossils allows geologists to further subdivide the eon into three shorter eras: the Paleozoic, Mesozoic, and Cenozoic.
The breaks between the Paleozoic and Mesozoic and the Mesozoic and Cenozoic eras represent two major extinction events that significantly reduced the number of organisms present on the planet.
Generally, you can see that this graph shows an increase in the number of genera with time, except for 5 major extinction events, the most significant of which occurred between the eras. Extinction can be due to various causes, all of which result in a dramatic change in some part of the Earth system that affects key populations of organisms.
So, summarizing a few points from Earth's early history. The oceans came from volcanic eruptions, comets, and asteroids. Our atmosphere was very different in the Archean. Earth's climate has fluctuated dramatically, and we have a recent record of evolutionary changes separated by dramatic extinctions.
We had one major learning objective for this lesson. How confident are you that you could complete this task?